Hello, we're back. Listen, last time we covered the basic graphs of sine, cosine, and tangent. This time we're going to mess with them a little bit numerically and see what happens. Okay, called transformations of the basic trig functions. Okay, and then I hope to show you, first of all, how to sketch graphs, and then what it's all good for. What's the applications of this, which is huge. Okay? Before we do that, let's look at last night's homework. Okay? Well, we were supposed to convert from radians to degrees. Now, I think it's important to note at this point that unless we see degrees, we're talking radians. Okay? For instance, in this problem, they want me to convert from 3 pi over 4 to what that would be in degrees. Okay? Let's see, what do we do? I'm going to divide by 2 pi being all the way around the circle, and then re-throw in all the way around the circle in degrees. So I'm dividing by 2 pi and multiplying by 360, because they're really the same thing. I'll end up with the same answer. Let's cancel the pi's, and let's see, what else can I cancel? I cancel the 2 with the 360. What do I get? 180. Any other canceling? A 4 with the 180. That's a 45 and a 1. And basically multiply, and hi, Mom, I get 135 degrees. Note that I have the degree symbol there. Okay, there's no radian symbol like an R. So once again, let me just mention, if you don't see anything, okay, how about the other way? What if I want to go backward from negative 135, it's a little bit different, to a radian measure? Well, this time I'm going to divide by 360 and multiply by 2 pi. Okay, now I'm cancel man. Here we go. Cancel. Well, I get 180 there. Any other canceling? How about the 135 with the 180? Okay, that's basically 45. Goes into that 3 times and that 4 times. So what do we got left here? We got a minus 3, a pi, and a 4. There's your answer. Minus 3 pi over 4. And that's in radians because I don't see any symbol. Okay? Do one more. Ooh, this is a hard one. Okay, we're supposed to not just convert, but we're also supposed to find the sine of 7 pi over 6 radians. Okay? Let's see. Let's convert it first. I'm going to divide by 2 pi and multiply by his degree equivalent, 360. Cancel. Let's see. Pi's get out of here. That's why I did it. Let's cancel the 2 with the 360. We get a 180. I think the 6 and the 180 can cancel. There we go. And that leaves me with a 7 and a 30. And the answer is 210. But I want the sine of that, the sine of 210. Okay? Well, let's see. That 210, where is 210? 210's almost, it's a little bit more than 180. Okay? So it's in the third quadrant, so I'm going to have to use a reference angle. Okay, let's see. This reference angle is going to be 30 because it's 30 more than 180. Okay, let me drop a perpendicular or throw up a perpendicular. Okay, and remember in this quadrant x is negative and y is negative. So this side will be negative x and this side will be negative y. Okay, the sine being the opposite over the hypotenuse being 1 in this unit circle, is going to be let's see, the sine will be negative y over 1. Okay, so it's going to be negative, whatever the negative sine of 210 is. Oh, I'm sorry, the sine of 30. Okay, and the sine of 30 is 0.5, so our answer is negative 0.5. Okay, that's the kind of thing we asked you to do in the homework. Okay, now let's get back to our basic curves that we showed you last time. Okay, the sine curve looks very much like this. Okay, it had a domain of any number. You put in any number you want, anything, any x that you could put in, and the range was a little bit different. You could only get numbers between negative 1 and 1, inclusive. Okay, you see it went down, came back, went up, came back, etc. Okay, now the sine, we're going to change it a little bit. I want you to get to know the sine wave, if you would, and it's only one wave. Okay, and it looks kind of like this. Okay, and if you look, if you turn sideways, got everything, it looks like an S. That's how I remember how to draw it. It looks like an S for sine wave, okay? And it really has three motions, right? 1, 2, 3, okay? So the way I remember it is I use the word spaghetti. Starts with an S, 3 syllables, spaghetti. Every time I draw it, I go spaghetti, spaghetti, okay? So remember that. As opposed to, because we're going to have to draw that later, okay? Let's look at the cosine, okay? The cosine, this is what it looked like. It had a domain, once again, of any number. You could put anything you wanted, and it would go on forever in every direction. That's going to be an advantage in the future. It had a similar range that it fluctuated pretty much between -1 and 1, okay? Now, the cosine wave looks very different if you go, you know, a full around the circle. The cosine doesn't start off at 0. It starts off at 1. At 0 degrees, or 0 radians, the cosine, the answer is 1, okay? So it starts off at 1, or I shouldn't say 1 because we're not always going to have a unit circle. It starts off at its highest point, okay? So one cycle looks kind of like this. Look at that bad boy. Now, here again, if you lay down and look, it looks like a C, doesn't it? Like the C for cosine. Kind of stretching it a little bit, but it looks like a C. And every time I draw it, I got to have a word. It's a 2-syllable word because you really go down and up, okay? So I use cuckoo, cuckoo, okay? So you'll be hearing that when we draw the cosine, okay? Let's look at the tangent. I got that last time. And the tangent, when we drew the lines and connected all those crazy points, looked like this. Now the tangent had a lot of holes in it, okay? So it's not going to be of great use to us in industry, as much anyway as the sine and cosine. So today we're only going to talk, I just wanted to show you that though, we'll talk about the sine and cosine, okay? Now, there are some fancy words that you're going to have to know before, so that when I use them you'll know what I'm talking about, okay? The first one is the word amplitude. The amplitude of something, as you can see, is the maximum height, okay, the height of a wave, as high as it gets, okay? And remember that distance can never be negative, okay? Another word we're going to talk about is the frequency. The frequency of a wave is how many times it goes through a cycle over 2 pi. Now, why are they using 2 pi? Remember that 2 pi is all the way around the circle, or 360 degrees in degree language. So how many times does it go, how many times do you get to ride the roller coaster, if you would? Or how many times do you do the S over a 2 pi period? Okay? Another word is the phase shift. We're going to be able to add the graph and move it left to right. The amount that we move it left to right will be called the phase shift. If we move it to the left, it'll be a negative phase shift. If we move it to the right in the positive direction, it'll be a positive phase shift. Okay? Now let's see what these look like pictorially. Okay? We take this graph. Let's see. It goes up, I hope you can see, it goes up about as high as 1. Okay? That's how high it is. You see how that distance there? That's the amplitude. Okay, that's what I mean. That distance there. That distance there. Okay? Now, it also goes down. Okay? The amplitude is 1 in this case. In this case, okay? Let's look at another one and see how they're the same. What is the amplitude of this guy? Well, how high does he go? Okay, we don't have a number on the graph for it. Well, he goes up 3. Or you mean 3. See how high that is? It goes up as high as 3. That's the amplitude. That'll always be it. It's also as low as it goes. In every case, they're all the same, okay? Don't think that it's going to go wider at some distance or something like that, okay? How about another one? Oh. So how's it going to affect the domain? It's not going to affect the domain in this case, but for this function, it's definitely going to affect the range, okay? Because now it doesn't go between -1 and 1. Now in this case, it goes between -3 and 3, okay? So, and of course changes it, okay? What about this one? What's the amplitude of this, okay? Well, you see how high it's going? It's going 0.5. Okay, so that is the amplitude. Did you notice something about where the amplitude always ends up? Okay, it always ends up the number right in front of the sign. Okay, and that'll always be the case, so you can rely on that. Every one of these little things is 0.5. Okay, up and down, whichever distance you go. Okay, The domain in this case, once again, of this curve will be all the real numbers, but the range this case will be going from negative 0.5 to positive 0.5. Okay, all the possible answers you can get out. Okay, now something different. Let's look at this one. It starts at, you could say, it starts at 0, because the S, the spaghetti S, starts at 0, and that's where it ends. The S ends at 2 pi, or it's about, remember that 2 pi is about 6.2 something, okay, 6.28. So that's where it ends up, okay? Well, I don't know if you can see, but that is the frequency. It goes through it one time. It goes through the roller coaster ride one time over the 2 pi period. Okay, so that's called the frequency. And the number in front of x always ends up being the frequency. Isn't that nice? Okay? This being one period, let's look at another one. Okay, now this one's way more, if you would, frequent. Okay? This one is as frequent as 3x. If we go from 0, where it starts, to 2 pi, which is, as I said, about 6 point blah, 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 something, okay, how many times do we get to do the S? Okay, well, let's see, 1, 2, 3 times, okay? So it shouldn't surprise you that the frequency in this case is 3, okay, the number, and it always is the number in front of x, okay? That's pretty cool, okay? That's one. Now this number of times that it goes through this roller coaster ride, or this spaghetti S, if you would, is called a period, okay? Now how are we going to, we can calculate a period, okay, by saying 1 over the frequency, okay? So if you know the frequency, you can find the period. 1 over the frequency times 2 pi. So 1/3 of 2 pi, in this case, is a period. Okay, or 2/3 pi, you could say. Okay, let's look at this one. What's the frequency of this one? It's not quite as often, if you would. Okay, it's 0.5. 0.5 is how frequent it occurs over a 2 pi period. It starts here, okay, and there's where 2 pi is, but it only makes the first part of the roller coaster ride. It doesn't finish the full S in that part. Okay. So it shouldn't surprise you that in this case the frequency is a lower number, and it is. It's the number in front of x, 0.5. Okay? What is 1 period? Well, once again, it's going to be 1 over the frequency. 1 over 0.5 times 2 pi. What is 1 over 0.5 is 2. Okay? 2 times 2 pi, the period of this, in other words, it took 4 pi to ride the whole roller coaster. Okay, so the period is, or to do the whole spaghetti S. Okay, that's the way I think of it. So that's the period. Okay, let's do another one. Okay, we start here, and this is a different word. If the sine of x starts here, the period begins at 0, and it ends there at about 2 pi. Okay, that's where it normally is. What if I had this graph, and it started there? Now it usually starts at 0, okay, but it's starting there and it's ending here. That's where the period is ending. Now normally it starts here, and normally, as I say, it starts at 0, and it's moved over a little bit. That moving over, okay, and it ends here, and it's moved over a little bit. That moving over, in this case, of +1 in the right direction, is called the phase shift. Okay? We've shifted the phase, in this case, in a positive direction. And I'm going to tell you later that if we have a number in front of the sign will be A, the number in front of x will be B, and another number sitting by itself, in this case -1, is C, the phase shift will always be -C over B. In this case, -1 over 1, minus of -1 over 1 is 1. So the phase shift, shouldn't surprise you in this case, is 1. Okay? What's the phase shift in this one? Ugh. Okay? Well, it normally starts at 0, and now it's going backward. We actually moved it to the left. Okay? In In this case, minus c over b would be the minus 4 over the 3 would be minus 4/3. And son of a gun, if you can see, that is where it's starting. Okay, usually starts here, right there, but the s is actually starting here now. Okay, so it is actually shifted minus 4/3, or minus 1 1/3 to the left. Okay, how about another one? What's the phase shift in this one? Well, you can see it there. Minus c over b would be minus of negative 2 over 3, which would end up being 2/3. Okay, did we do that in this case? Normally it would start at 0. The sign normally starts at 0. But it started over here. Okay, it shifted 2/3. Okay, so in summary, if we have an equation of the form a sine bx plus c, the amplitude will always be the number a, the number in front of the sign. The frequency, now this is how frequent you get to do the spaghetti curve over 2 pi, or over 360 degrees, is b, the number in front of x. Okay? And the period is how long it takes on your graph to finish your spaghetti curve, is 1 over that times 2 pi, 1 over b times 2 pi. And our phase shift, the amount we moved left to right, is always minus c over b. Okay? Let's sketch this. Let's sketch one. Okay, and that's what I'm going to ask you to do. Okay, let's sketch the sine of x plus 1. We'll figure out the amplitude. The amplitude is the number in front of sine. The frequency would be the number in front of x, which is 1. The period would be 1 over that times 2 pi, which is a pretty simple one. This is just 2 pi. And the phase shift is minus c over b, which in this case is minus 1. A little bit different. Okay? What I typically do is, first thing I do is get the phase shift. Okay? Find out where it would start, where one spaghetti curve would start. Okay? Find out where it would end. Go 2 pi away. Now I've got to get a spaghetti curve between those two spots. Okay? Now how high does it have to be? The amplitude, which is the number in front of sine, has got to be 1. So I'll draw it. Ready? Spaghetti. I got to do another one. Spaghetti. I only get the spa in this case. Okay, and that's kind of the way that I would do it. Okay, let's try this with a calculator, if for no other reason, just to check and make sure we did it right. Okay, get your calculator out. Okay, and don't forget these buttons. Okay, let's remember. We need to know where the mode button is. Okay, we'll need to know where the y equals button. Find that on your calculator. The x button, I call it the variable button. Okay, find that. The graph button, remember we used that last time. The zoom, okay, that's if we're in too close or out too far. The parentheses we'll need, and the on button. Okay, let me try it first, and then you do it. Okay? Let's see. I'm going to clear out what we got. Now, the first thing I'm going to do is make sure that I'm in Radian mode, okay, which I'm not. Okay, because remember, every one of these, you don't see any degrees, so we're going to have to be in Radian mode. So let me cursor down, hit mode, cursor down to Radian, and hit enter. And you should do that, and then we'll clear out. Okay, now I know I'm hunky-dinky. Okay, and I'll hit the y equals button. Okay, I got something from the last time, so I'll clear it. Okay, and I'm going to type sine, and I'm going to hit the x button, plus 1, and I'll need the parentheses so it doesn't take the sine of x and then add 1 to it. So that's taking actually 1. Okay, and let's tell it to graph by hitting the graph button. Now this is a mess. Okay, what's the problem? I suspect that we're zoomed in too close or too far. Okay, so what we have to do every time, that'll fix it, is to zoom to Trig. Okay, I guess we're out way too far. Zoom. You don't have to cursor down to Trig. You could just hit 7, but I'll do that. And hi, Mom. Now it gets to the right place. Apparently I was out too far that time. Okay, and it looks very much like what I had sketched. Okay. Okay, now you try it. I'll clear out. Okay, what are the steps? We'll go to full view. Okay, what are the steps? You want to get your mode, make sure you're in Radian mode. and then come out with a clear. Type your y equals button, sign of x plus 1. Don't forget your parentheses. You'll have the sign button, the x button, the plus 1 in the parentheses. Then tell it to graph. Now, if it looks terrible, it may look great, okay? You might have to zoom trig, okay? Zoom, remember, trig is the 7th one down. Okay? If you're happy with it, then we're ready to move on to the next one, so I would have you clear out, okay? Let's look at another one. We'll sketch, okay? Let's sketch y equals 1.5 sine of 2x plus 6. Ugh, that looks tough. Okay, well, don't be afraid. Figure out what each of the things are first. The other sine is 1.5. Okay, that's how high it gets. The frequency over 2 pi in front of x. Okay, that's how often it's going to occur over the 2 pi period. Or we could say a period. It's always nice to calculate a period, how wide the spaghetti s is going to be. That would be 1 over b, or 1 over 2 times 2 pi, which in this case, we do a little calculation, comes out to 1 pi. Okay, and what was the other one? The phase shift, which is always minus c over b, which in this case, minus 6 over 2 is minus 3. So we're going to be moving to the left in this case. Okay, let me see. Okay, get my spaghetti ready. Let's see. It's a minus 3 phase shift. Okay, it's going to start at minus 3. Now, why minus 3 there? Remember what minus 1 pi is. Minus 1 pi is minus 3.14 something. Okay, so I'm pretty close with minus 3 there. Okay, now where's it going to end? Go 2 pi away. No, I'm sorry. We have to go 1 pi, because we calculated the end of an s being 1 pi distance. Okay, now how high do I have to make this? What kind of amplitude do I have to make this spaghetti s? Okay, well, it's 1.5, so it's going to be that high. So let me start at my starting point and go. Oh, it's a sine, so I'm going to start at the line. Spaghetti. Let me do another one. Spaghetti. Help me out, Sam. Spaghetti. He said it. Good. Okay. And I'm going to go backward. Okay. Good. There we go. And that's kind of what it looks like. Okay. I always do the, what do? We figure out the phase shift, figure out a period, and then figure out how high I have to make it. Let's try it with a graph to check it. You know what I'm going to be checking? I'm going to be checking to make sure that it's kind of a little bit over like this one. Okay? Let's see. Let me do it, and then you'll do it. Okay? Let's see. I'm going to put in here y equals. I know I'm already in, from last time, that I'm in radian mode. We should have checked that, but I know I'm in radian mode, so I'm not going to check that this time. Okay? Y equals 1.5 sine, okay, of 2x, don't have to say 2 times x on these calculators, 2x plus 6. Okay, do your parentheses and tell it to graph. Okay, now at this point, it looks kind of like it, but I'm a little bit nervous. I'm a little bit nervous as to whether this point is shifted over properly or not. Okay, so let me zoom in just for laughs. Okay, hit zoom, and number 2 says zoom in. Okay, and I wouldn't want to see it like that. But gun, it looks just like my picture. It's shifted over a little bit, so I think I'm hunky-dinky there. Okay, let me go back to zoom trig and give you your chance. Okay? Okay, you try it. Go to full view. You'll say y equals. Got to type all this. This is a mouthful. Okay, you got to get all that in there. 1.5 sine of 2. Use your x button plus 6. Don't forget your parentheses. Okay, and then hit your graph button. Okay, if you're happy with it, you won't have to do your zoom trig. Okay, and those are the buttons you would hit to do it. And when you're done, how do we get the heck out anyway? Okay, you'll hit your clear. Okay, let's do a couple more. Okay, because you got to get pretty good at this. Okay, we're going to sketch a cosine this time. Y equals 0.5 cosine. The cosine works very similar, except remember the cosine was cuckoo, it was a c, okay? Okay, the amplitude is 0.5, the number in front of cosine. The frequency over 2 pi is that number in front of x, which makes the period 1 over that times 2 pi, so we got to get this c drawn in a ½ a pi period, okay? Now, ½ a pi times 4 1/4 of 2 pi. Yeah, that's right, 1/2 of pi. Okay, and then the phase shift is going to be the negative of a negative, which is going to be plus 1/4 here. Okay? Okay, let's see if we can do this. I'm going to remember my period is 1/2 of a pi. Okay? Well, this time, I'm going to start at plus 1/4. Okay, now that may not look like plus 1/4 on this graph, but remember, 1 pi, what you're seeing there, is really 3 point something. Okay, so that's about 1/4. Now, where is it going to end? A little bit more than 1/2 a pi, because I had shifted over. Now, let's see. This is the cosine. You got to remember it's the cosine, okay? So we're going to sketch a cosine of amplitude 0.5. It's not going to be very high. It's not going to start at the 0 point, okay? It's going to be a C. So it's going to start right here at its highest point. Remember, that's how the cosine is different. So we'll start there, and let's do our C. Remember? Cuckoo. Again. Cuckoo. 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 Uh-oh, now we got to go back. Is that a oo-coo? Oo-coo. Oo-coo. Sam? Good one. All right. Okay. Cuckoo. Okay. See, not too bad. Okay. You see how we get an amplitude of 0.5. Let's graph it. Okay. Let me try it, then you try it. Okay. Let's see. I'll clear out. Y equals. I'm going to hit clear to get rid of all this garbage. Okay. 0.5 cosine of 4x minus 1. 4x minus 1, don't forget your parentheses, and tell that baby to graph. Oh, remember from last time? I think I'm in too close here. Okay? Can you see it? I think I'm in too close. But remember the fix all here. No, I'm out too far. I'm sorry. The fix all is zoom trig. Oh, that is 2. That is right. Okay, that is 2 phases. Okay, and it appears just like the one I drew, so I'm hunky-dinky. You see where my cuckoo started, so I'm looking good. Now you try it. Okay, let's see. What are you going to do? Y equals 0.5 cosine 4x minus 1. Oof, looks hard. Show that one to your mom. Okay, graph. Hit the graph button. And if you don't like it, and you have time, it's probably already zoomed to trig. We'll stay at that zoom for the rest of the class. Okay, zoom trig. Okay? Looks very much like it. Now, it's not going to be the end all, because when you do this on a test, you're going to have to be able to sketch. You're going to have to show me the little critical points, the little points on, you can't just copy what's on your calculator. Okay? So you're going to have to know what you're doing. The calculator's a great check, though. Okay? Okay, clear that out. And I'm going to have you do, let's do it together, just in case. We'll do this one. This one's a little bit harder, okay, because it's a negative, okay? Let's see. What's the amplitude of this one to be? People say, well, it'd be negative 2. Well, you can't have a negative distance, okay? So it'll be positive. It's the absolute value of A, if you would. Okay, so the amplitude will be 2. This will be pretty high. The frequency over 2 pi will be 2. That's the number in front of x, which means the period is 1 over that times 2 pi. Well, at least it's easy in this case. It's the period, every 1 pi, I've got to do a cosine. I've got to do a cuckoo, okay? And then the phase shift is minus c over b, or minus 3 over 2. So we're going to move to the left, minus 3/2, okay? Let's take a look at how I would sketch it, okay? I put my pi's out there. I know it begins at minus 3 over 2. Now, I find that on the graph, remembering that pi is 3.14, so minus 3.14 is going to be, and minus 3 over 2 is 1.5. So that's about right, minus 1.5. Okay? And the end of a period, 1 pi away, okay, it's going to be that. Now I've got to do a cuckoo, a C cuckoo starting at that point. Okay? However, got to remember it's the cosine, but a little bit different here. This is a negative. So we're going to switch the cuckoo upside down. Okay? Switch the cuckoo upside down, and here's what it's going to look like. Okay, we'll sketch it. Instead of starting at its highest point, because of the negative, we're going to start at its lowest point. Cuckoo, cuckoo. Okay, let's go back the other way. Cuckoo. Do we have any more on the other side? Coo. Okay, you get the idea? Okay, it's because the negative makes it kind of a mirror of itself. Okay? Okay, I'll give you a chance to do this. I'm not going to do it. You can do this on your own. y equals negative 2 cosine 2x plus 3. This will be a great check. Okay, you'll be able to see, you know, because you might have screwed up that negative, but the calculator would have caught you in this case, I would hope. That's why I want you to do it with the calculator. Hit your graph button, and if you need to, do your zoom trig. Okay? Okay, clear that out. Let's work backwards. Okay? Let's guess what this sine equation is. Okay? This is a sine now. We've got to guess what this is. What's going to help us? Okay? It's got to be of this form. Y equals some number times sine, you know, bx plus c. Okay? Let's see. Well, what's the amplitude? The amplitude is how high it is. You can see right away. The amplitude is 4. So A is 4. That's going to help me out. Okay? What's the phase shift? Ooh, that's minus c over b. But at least, remember where the sine started off. So this sine is starting off where it normally starts at 0. It's the s, the spaghetti s is starting off at 1. Okay? So the phase shift ends up being 1. Okay? The frequency over 2 pi, what's the frequency over 2 pi? If we go from, if we look at how between 0 and 2 pi, which is 6, instead I'm going to look at between 1 and 7, okay, which is about 2 pi. Remember that 2 pi is 2 times 3.14, which is about 6.2 something, okay? So if I start here and go to the S thing, it looks like my frequency is 1 as well, okay? So a possible one for this would be y equals 4 sine 1x minus 1. Now why did I get minus 1? Because the phase shift, it appears to have moved over to the right, okay? So, and the phase shift is minus c over b, so I needed a minus 1 there. And actually, if you think about this, I could do another one, I guess. Couldn't I do 4 sine 1x minus 7.2? Where am I getting 7.2? Instead of starting at minus 1 or starting at 1, couldn't we be starting over here at 7.2? Okay, so it's shifted in that direction. Okay, this is another way. Or you could say, let's shift the other way. Okay, and we could use plus 5.3. I'm looking right here, and the sine curve, the spaghetti s, started at negative 5.3, which would make the phase shift, you know, I'd have to make that a positive 5.3 to have the phase shift work out. So there's another answer. There's a lot of answers to this one. Do another one. Okay, guess the cosine of this one. Well, the cosine starts at its highest point. Okay? Let's see. The amplitude is 4, again in this case. The frequency over 2 pi starts up here. Let's see. Over 2 pi, I'm going to go from, well, let's see. It's the cosine. I'm going to start here. That's where it's starting. The phase shift, it normally starts at 0. I'm going to start at about, it looks like about 2.5. Okay? So the phase shift is going to be negative 2.5. So I'm going to use 4 cosine 1x minus 2.5, okay, because I went in the right direction. Could I have it instead, the cosine start here, okay, which would get me at about let's say negative 3.7. So I'd have to use a positive 3.7 in the calculation, in the equation. Okay, it's another way to look at it. Okay? Okay, one more. Look at this. This one's frequent as a mug. Okay? Let's see. The amplitude is 2.5. The phase shift, well, it usually starts at 0, and it's starting at 0. So this one's not too bad. The phase shift is nothing. Okay, so minus c over b is nothing, which leads me to believe that c is nothing. Okay? Or 0. And the frequency, now this one's frequent. If we go from 0 all the way over to 2 pi or over to 6.2, it goes through the S curve 1, 2, 3 times. So the frequency is 3, or b is 3. Okay, frequency over 2 pi will be 3 in this case. So I'll just fill those numbers in, and I get y equals 2.5 sine of 3x. It's a possible guess. Okay? Okay, now, what is all this good for? Why am I driving you crazy with this stuff? This is very useful in industry to make these changes to this to these equations and do stuff with it. Let me show you what we would do. Okay? Okay, the Cognitive Technologies Corporation, which is a local company in Rockville, puts out this real nice Trig Explorer program, and I want to show you some of the uses that it demonstrates. Okay, it does a whole lot that I'm not going to show you. So we're going to go into actual plotting. Okay, let's plot this baby. Okay, this is going to give me the option to plot many things. I just want you to note that a machine, this being a computer, of course, can quickly, based on changing these numbers, A, B, and C, can quickly change the graph. For instance, if I leave them as 1, 1, and 0, which is basically the normal sine curve, I can graph the sine curve, and it'll do it for me quite fast. Okay? Let's do the normal cosine curve. See what remember that one? That one starts at its highest point, which in this case is 1. Okay? Let's clear that out. How about if we change the amplitude to 2? Okay? And let's look at the sine, see how that changes. Just that fast. Okay, now it's high, as you can see. Okay? And let's look at let's clear it out. We'll look at the cosine of that. Okay? Same thing, except the cosine, remember, starts at its highest point and works its way all the way to 2 pi, known downtown as 360 degrees. Okay? What if we get smaller, a smaller amplitude? I'll say 0.5. I think we used an example like that. The sine, okay, it still starts here, but it only goes up to 0.5. Okay? And it still finishes at 360. Okay? The cosine would be the same thing, except it would start up here, do your coo-coo, and end up at 360 degrees. Okay? Now let's do a phase shift on this bad boy. Okay? So we're going to leave this at 1, and the phase shift, I'm going to put in a crazy number. You say, where am I getting this number? Negative 3.14. Do you recognize that number? That's negative pi. Okay? Which means I'm going to move, if C in the equation is negative, the phase shift, which is negative C over B, is going to end up being in the positive direction. Okay? Let's take a look. Okay? Now, where did it, usually the sine starts here, but here the sine starts here at 1 pi. Spaghetti. Okay? Let's look at the cosine. Okay, normally the cosine starts at its highest point here, but now it's starting here. Coo, coo. Okay, it gets around the whole 2 pi distance. Okay? What about a couple more? Let's look at, what if we put this as 1? Let's put this back to no phase shift. Okay? And let's make this, the B, a 2. Remember what the B was? That was the frequency. Okay? It's just a little bit more frequent for the sine. Starts off here, spaghetti, spaghetti, okay, all the way to 360. You went twice that time. How about the cosine? Spaghetti. Oh, no, not spaghetti. Cuckoo, cuckoo. Okay, it went twice. Okay? How about, let's get crazy here. How about we put in a 5 for the frequency? That means that thing has to go 5 times. Okay, let's see. Can it do it? I'm going to have like a whole pasta salad here. Spaghetti, 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 spaghetti. 5 times to 360. Okay? And oh, you know what you're going to hear on the cosine. Let's clear it out. What time is it? 5 o'clock? Cuckoo, 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 cuckoo. Son of a gun. It did go 5 times between 0 and 2 pi. Okay? So we can, the point I'm trying to make here is that a machine putting in various numbers can quickly create and change the graph that you're seeing. Okay? We know that. Well, let's look at how this relates to sound now. Okay? Okay, we can actually graph a sound. Okay? Which is pretty cool. Let me show you how this would happen. Okay? If we take a sound, I'm going to turn the volume up a little bit. Look what's happening. Okay? Can you hear the sound? Now, what I want you to notice is as we adjust the frequency of the sound. Well, we're really adjusting the frequency of the sound. We can adjust the frequency of the graph. What happens to the tone? You ready? Let me adjust it up this way. What if I adjust it back this way? Now, some of you are tone deaf, but are you noticing that what changes as the frequency goes down is that the pitch goes down, and as the frequency goes up, the pitch goes up. Now, let's look at the frequency of this graph is changing. Let's look at the amplitude of this graph. See how high it is. I'm going to make it a little bit higher and see if you can hear the difference. It's a little bit louder. It's even louder. Now the pitch hasn't changed, but it's louder. And what happens is, as the amplitude gets higher, better turn it down, it gets quieter. As the amplitude gets smaller, teeny, it's just a whisper. Once again, I can change the pitch of that by changing the frequency. How frequent can we make this thing? Let's see. Oh. Okay, that's the idea. If a machine can take sound and make a graph out of it, and not only make a graph out of it, but a specific graph that has different amplitudes and different frequencies, and we can look at that graph and read different changes, well, we can attach sensors to things. You ever seen a sensor attached to somebody's chest, or perhaps sensors attached to their head, or sensors attached to the ground? Okay, and we can have those sensors listen, okay, and they can measure, and we can take that sound and then put it on a graph. Okay, what are the kind of things that we can simulate in nature? And we know that graph's going to be a sine or a cosine function. Okay, well, of course, sound waves, we just did that. Okay, ocean waves, okay, they travel in sine waves. Now they change, okay, but the sensors will let us know when they're going to change. Earthquake waves, earthquakes travel in, okay, in waves, of course, okay. Light waves, they actually travel in waves, so you're not going to measure sound there, but you'll be measuring something, brightness, various things, okay, color, etc. Radio waves, they travel in sine waves, okay. Now, if we transform these things, what changes occur? Okay, what are we measuring, is what I'm saying, okay. Well, we know from our example, when we change a sound, the volume and the pitch, and actually the duration, how long the sound goes, it's almost like a note, if you would, okay. What happens with ocean waves when you change these things? Well, the height known downtown as amplitude, as we know, we surfers know, okay, we're all looking for that. How frequent the waves occur, and wouldn't it be a dream to have a nice long high wave? That's the way they are in Hawaii, okay, but that's the kind of thing you would study, okay. Great thing to study with earthquakes is not only the strength of the earthquake, but how frequent the earthquakes or the quakes themselves are going to occur. Think about it. It goes in a wave, okay. It would be great not just to measure it, but perhaps to use that measurement to predict things, to get out of the way, at least, for nothing else, okay? Light waves, what happens when things change? Well, we get different colors, and we get different brightnesses, okay, when we change the frequency and the amplitude, okay? And radio waves, hey, guess what? That's how you're tuning in stations, okay? You're changing the frequency and the amplitude of your radio wave, okay? Now, we can actually simulate these things, a calculator can, or a machine, a computer can simulate these things, okay? For instance, I made a graph of, sometimes it's a little bit more complicated, I made a graph of this equation, which is a kind of a union of two sine, the sum of two sine functions, okay? And it created this sort of graph, okay? It looks not exactly a sine wave, there's a little bit of bend in it from that other sine function. But if we put sensors on somebody and we listen to their brain waves, we can make, without digging into their head, we can find out, you know, what's wrong with them or what's right with them, or whether they're lying or not. You can do that, okay? In fact, I went to the doctor the other day, and it doesn't always work. He gave me my a picture of my brain waves, and I couldn't figure out a sine wave for that. So it doesn't always work. But okay, a great use of this is, I know my wife's a cardiac nurse, and they listen to people's hearts, and they actually have a name for each of the little curves here. They call it a P wave, an R wave, an S wave, each of these little turns here. Okay, and they can look at them on the monitor. They call it a monitor. It's like your graph. And they can tell, without digging into your heart or opening up your chest, whether you have, not only whether you have a healthy heart or an unhealthy heart, but if you do have an unhealthy heart, they can tell that, for instance, oh yeah, that valve in your right ventricle is blocked. Okay, they can tell that by looking at the graph. It's wonderful that they can use this. Okay? Anyway, that's what they use this stuff for. Now, your job at this point is to do homework number 6 and then review assignment number 7. Okay? Now, you really want to do, I want to stress, you really want to do review assignment number 7 because, number 1, it's worth twice as many points if you look at your syllabus as any of the homeworks. And the reason for that is I'm very predictable. I don't like to surprise anybody on tests. After that, you're supposed to go and take the midterm exam. Okay? And the midterm exam, I might as well tell you, no surprises, looks just like the review assignment number 7. The numbers have changed, okay? But if you don't do review assignment number 7, you're gonna have trouble with the exam. Or you might not, okay? But you want to do assignment number 7, the review assignment, because it looks just like the midterm. And if you don't know how to do something on there, by all means, email me, okay, or call me, okay? So that's why I make the review worth so much. And then go to the assessment center, take the midterm exam, and we'll pick it up at the next time. Okay? Remember now, if you have trouble, you can always go to the home page, which is www.mc.cc.md.us/Witte. Okay? And there you can get the grade policy. You can get the answers. Okay, but you're going to have to show me all the work if you want credit for this. And you can even view what you've just seen today over the computer, step by step, maybe perhaps slowing it down for yourself. Okay? So until next time, thank you very much.